Okay, so today, welcome back to our ICQ YouTube channel. Today, we are interviewing Nicolas Biver from the Observatoire de Paris in Meudon, France. And so let's, we have our usual team members, Casper, Charles, Carl, and Mike Meyer from Germany today, as well as myself, Dan Green. So Nicolas, I'll start by asking you to just give a little brief background about yourself. Growing up, when did you become interested in astronomy, and a little bit about your educational background?
Okay, so I started being interested in astronomy in 1983. I can even say more or less in October 1983, I suddenly began at a nearly very precise date. Actually, I had my own small refractor telescope with an astronomy club in the surroundings where I'm living. But at that time, I was at a school in parallel. I had normal, studies but I did astronomy as an amateur for a while until I did my PhD between 93 and 1997, and then that's when I really started doing professional astronomy. But from 1983 until now, I've been doing in parallel amateur astronomy. And also before my PhD in astrophysics, I did also what we call engineering high school in France. This gives you a diploma with which you can do either, working in a company, building rockets, for example, or working in in banks or whatever. But at the end of this 3-year formation, then I switched to the research direction, doing a PhD, while many other people are doing, as I said, they're working in business companies and so on. So it's a rough, presentation of what is my background, if you want. After I can give more detail after my PhD, when I spent 3 years as a postdoc in Hawaii, 1 year in the Netherlands at the European Space Agency before getting my current permanent position in France in 2002.
Okay. Carl?
Yeah, so you kind of take part in something that's kind of becoming a long-lost art form, in that you ground polished and figured your own optics, and you've gotten really good at that. And we were just wondering, were you inspired by your fellow countryman, Jean Texahu?
Well, I could say partly yes, partly no. Actually, I did grind one of my telescope mirrors, the 10-inch one. It's actually the one I brought to Hawaii for 3 years. But for the others, the first telescope I made, I just bought the 8-inch mirror actually from a company in the US. We bought it just after a trip with my family in 1988. And the next one, the biggest one I have now, which is a 40 centimeter, 16-inch in diameter, it was ground by someone I know. We made it from his company, but it's no longer a grinding mirror actually, so it was made in France. It's not made in a factory, but 16-inch telescope is kind of big mirror, to do it yourself. So, but I think in the question you are asking if I did it on my own at home, or if I did it within an astronomy club, more or less. In fact, I did it with what we call the Commission des Instruments of the French Astronomical Society, which has I think it was founded by Jean Texero in the 1960s or so on. And so there is a long history of grinding mirror at the French Astronomical Society. There's a place in Paris where we do grind our mirror. So I didn't do it alone, but I did it in that very place with lots of other people grinding their mirror with the council you need to do it correctly. And so it's not as difficult as doing it on your own at home.
Okay. Well, we're going to ask you a little bit about your visual observation of comets before we get into your radio observations. Charles, you want to pick it up?
Oh, you're muted, Charles.
Charles, we can't hear you.
I apologize.
Okay.
Okay. According to the Cobb's Comet Observation website, you are number 2 in the all-time list of comet magnitude observers with 5,355 observations. In order to make so many observations, one needs to observe for many years at a constant rate. How have you kept your enthusiasm for visual observations of comets since you started in 93, 83?
93. Well, it was
93.
93 for comets. Yeah. It's kind of addiction. I can't tell you why I'm doing this, but it's also the way I started doing amateur astronomy 10 years before in 1983. I mean, from the beginning and now, I cannot help with not observing when the sky is clear. So it's just a kind of addiction. I don't have a family, so it doesn't prevent me from doing observation as soon as I can. So I'm surprised that I'm the second one in the number of observation, because I see even for example, you, Charles, you have done so many comet observation. I'm surprised that
some of mine are not in the Cobb's database.
Okay. Well, I have also some backlog. I have many observations from the last 1 or 2 years that I need to send back send to the Cobb's database. But yeah, I think since 1993, when I started doing visual estimate following the normal rules, because I've been observing comets since Halley's comet in 1985, but I started doing my visual estimate in 1983, and I think since that date, I've been trying to observe comet at least every new moon for the last 30 years. So probably it's the sum of 30 years of observation and several observations per month that makes this total amount of observation. I'm surprised that it's already so many, but I still have some or many from this year, and I think maybe even last year to send around. So.
Yeah. Okay, Mike.
Yeah. Question about your methodology. So what are the instruments you're usually using, and do you have special observing techniques that you use for it, and has it changed over the years? So I started in 1987, you in 1993, and for me it has changed a little bit from my humble beginnings until now. So yeah.
Well, maybe not so much. I'm still doing visual estimates, probably not in a very different way from what I was doing 30 years ago. So some with the bigger scope I have, because I cannot take with me all the different telescopes when I go observing. But I always take the pair of binoculars when you have a comet that reaches magnitude 9 or 8, then if I can see it with binoculars, I mean, following the rule, I mean, you have to use the smallest instrument you can. But sometimes I have only the binoculars on the 40-centimeter telescope, so I do with what I have. I must say also that that's kind of a hobby, but every time I observe something, I make a drawing. So I have a drawing, even if it's just a fuzzy spot for each observation of the comet. Nearly for each magnitude estimate, I have a corresponding drawing on the notes, of course, to do the magnitude estimates. And what has been changing a bit for the last 5-6 years is that now I have also this kind of DSLR cameras, Sony Alpha 7S, which is quite efficient at taking cometary images. So I quite often, for the brighter comet, switch from the eyepiece to the camera and vice versa when I do my observations. So I have also, images on trying also to make a magnitude estimate from the images and eventually of F rows. I mean, for those who know what is this parameter.
Okay. Casper?
Yeah. Have you also done any CCD observations?
So I said it's not CCD because it's a digital camera, but it's not very different from CCD, but it's color images. So okay. I'm not using CCD plus filters. I'm using the digital camera. I mean, the principle is not so far, but I don't have a CCD camera because when I'm doing these pictures, is my 16-inch telescope. I have not a full equatorial mount. It's a Dobsonian I put on the equatorial table, so I can do short exposures, but it's not a setup that you will use for a CCD under a dome and so on. So,
I think. And have you used any other telescopes over the years for visual work? I guess, you know, sometimes in a star party or in an observatory, there's like a very large aperture instrument, and you get to slew it to a particular comet that is bright. Have you used any larger instruments over the years?
Larger instrument once or a few times in a star party where I know another amateur astronomer in France who built his own 1 meter telescope. So I happened to observe a few comets in 1 meter telescope. But usually I have also my 16-inch, the 40 centimeter also there. So I'm more using my 40 centimeter telescope to do this regular, comet observation. And after, when you have a bigger telescope, you use it to look at nice nebula and so on. But I should mention there's another telescope that I've been used, and some people at some point they thought it was my telescope. It's not mine. It's just a small Celestron 8, which is at the radio telescope in Spain. So it was bought like 40 years ago for the staff of the observatory, but very few people know about this telescope or use it. I am one of the very few users of this telescope that I'm using when I'm there because I cannot bring my own telescope. So, there's this 8-inch telescope that I can use to observe some comets. Why I am or not observing with the radio telescope, depending on how busy I am.
Is it at the IRAM site that?
Yeah, at the IRAM in Spain. Yeah.
Okay.
So where do you do your visual observing? Aren't the skies pretty light polluted from Paris?
Yes, I'm doing it at many different places. Most often during the year, my main tool is my car. I put the telescope in the trunk of the car. I drive like 50, 60 kilometers away from Paris. And there the sky is, it's not perfect sky, but you can see the Milky Way on part of the sky. It's dark enough to see a diffuse comet and to take pictures. So for some comets, the most recent observation I did was just in Versailles. It was the last outburst of comet 12P Pons-Brooks because it was bright and very condensed. So that's I can do 5 minutes from home. But when I have to drive, it's a 1 hour drive. So it's
yeah.
And also during summer and sometimes also for 1 week during spring, I go to a star party where we have really dark skies. And of course, I also bring my telescope, and that's when I observe nearly every night when it's possible to observe.
Can I ask a follow-up?
Yeah.
When you say really dark skies, what's your limiting magnitude? Do you know?
I think the limiting magnitude is a bit subjective. I would say it's about 6.5, 6.6 for me. If you use the sky quality meter, it's about 21.5. So I don't. Well,
okay.
It's a bit subjective, and it's dark skies. But where I go in the Alps, it's not like the sky you get on Mauna Kea or in Chile. Where I happen also to do some observation with one of my smaller telescope. You can clearly see the Milky Way, but close to the horizon, the Milky Way is not as well defined as you will see at a higher elevation.
The reason I asked was because there is perhaps a misconception over here in the United States that there are no good observing sites on the continent. I mean, typically.
Yeah, I
That
can tell you
sounds
that's not true. There are some good dark sky sites in Europe.
Yeah, well,
well, not in the mountains. I'm talking about
Yeah.
easily. Okay, well, good, fair enough.
yeah, of course, it's not the best skies I've seen. Sometimes I have some souvenirs of some very few opportunities. Once it was on Mauna Kea in 2012, I think, when you could see, I mean, all the dark nebula in the Milky Way in a small telescope. And of course, it's not as good when I go in the Southern Alps. I mean, it's good enough, I think, for comets. I mean, the difference when you estimate the magnitude of a comet is not that big, I would say, between those two kinds of skies.
It is kind of depressing when you see the nighttime satellite view of Europe with all the lights, but there are a few dark spots here and there.
Yeah, well, I don't know if France is the worst place, but if you go to Netherlands, where I lived for 1 year, then it's full.
Yeah. All right, Carl.
Muted, Carl.
Yep, you'd unmute first. Nowadays, we're in this era of, multiple spacecraft missions going to comets. We have all sky surveys that are, doing photographic observations of comets as well as other things in the sky. How do you feel that amateur comet observations, whether they're visual or digital, are still useful for studying comets? And how can amateur observations better support the work of the professionals?
Well, I think it's a matter of follow-up of discoveries. I mean, these surveys are mostly doing the job of discoveries. I think some, like ZTF, is doing a kind of survey also of the outbursts, for example, of comets on like Kelly, I think, is doing. But if you look at the long trend of estimating the global brightness of a comet, total magnitude, on which actually we most often, base our prediction for having a comet that is worth investigating with professional means. I mean, we need, these visual estimates of the magnitudes. I think there's a kind of consistency in estimating the total brightness of a comet for over tens of years or decades or even centuries that you don't have with the CCD techniques or other, surveys or whatever.
So I was happy to see I think it was your most recent 67P paper, you actually have a figure of AFRO measurements that you made with your, I guess, the red band, the red channel of your DSLR. Can you talk a little more about that experience? Because it looks great.
Yeah, well, I think it should be taken with caution. I'm not doing it in the very professional way because I'm just using the red layer of the DSLR. I think recently I compared what I'm getting on the very gassy comet, and I think there's too much leak from the gas emissions. For the very gassy comet, but comet 67P is not so gassy, so I think the difference is not big. So, but that's I was not an expert on AFRO before, but I just read a few things about AFRO, how you can compute it, and I just noticed that in fact you can more or less do this computation not in a not too difficult way, just using the stars you have in the field of view. You don't need to take a calibrated spectrum of flux photometry on a standard star. You can do it like you do magnitude estimates on your images, and you get a relatively good estimate or AFRO, and that's of course the advantage of AFRO compared to the magnitude that you are no longer sensitive or the problem of how big is your coma in reality. So that's something I think we should more and more train amateurs to measurement of AFRO, because there's always a strong debate about measuring the total magnitude. I'm sure, and Charles, we had an exchange on Comet mailing list, about 46P, I think, about this. How big is the coma and how big is the bias, because you underestimate the size of the coma. And when you do AFRO measurement, you no longer care about the size of the coma. So that's a good and interesting point.
Sorry, I had my microphone turned off. Predictions of brightness, of course, are important for all astronomers, whether amateur or professional, because you need to know if you can go out and observe a comet, if it's a certain brightness, for whatever purpose it is that you're actually looking at the comets. So the Observatory of Paris has a long history in cometary science, and so you have people who have worked with you there in radio astronomy of comets, like Dominique Bocquely-Marvan and Jacques Crevissier. Can you tell us a little bit about the history of your group, how it started and how long it's been going?
For sure, yeah. Actually, I asked the question a bit to Dominique yesterday, because in fact, this long history of comet science at Paris Observatory started a while before me. She said, it started exactly with comet Kohoutek in 1973, when they did the first detection, spectroscopic detection of OH with the Nancy radio telescope in a comet. So at that time, it was done by people like François Biraud, Jacques Cazès, and Eric Gérard. And Eric Gérard was the supervisor of Jacques Crevissier and Dominique's thesis. And, so they started, doing science on comets a while, 20 years before. Actually, I started my PhD at the observatory. But after came, the international Alley Watch campaign, in which Eric Gérard took a lot of, he worked on it for a lot. And that's the time when also, Dominique did her PhD, and then when also the millimeter and sub-millimeter telescope started to open, and on the IRAM 30-meter telescope, we were talking a bit before, and we may talk a bit after. Did its first observation of a comet in 1985, and that was Halley's comet. So actually, the team strengthened around that time, and another person who worked after in Bordeaux did his PhD on comets. Also at that time was Didier Despois. So that's when really the big team of comet specialists, comet radio and infrared specialists started to work on comets. It was around the 80s, maybe 1985 to 1990, and I arrived in 1993. First doing a training period, and after doing my PhD in the team. Unfortunately, during my PhD came Hyakutake on Hale-Bopp's comet, and of course, that was a great opportunity. To do science from the ground on bright comets, and after, of course, we had the Rosetta mission 20 years later.
Okay, Mike.
Yeah, following up on that, in 2018, you've actually published a paper with Dominique in A&A, and where some of your drawings of Hale-Bopp were shown. So what would you say? Are there certain advantages with drawings over photographs, especially for the inner coma morphology?
Well, it was a kind of also attempt to see if I can put my drawing in a scientific publication. Apparently, the referee didn't complain. And the idea, in fact, is that I had observed, Hale-Bopp comet, for many days. Actually, we were fortunate that actually the spring of '97 was really, there was a drought actually in France. And I was nearly able to observe the comet every night during a month and a half or even more. So I had images at that time. We didn't have digital cameras. Some had CCDs, but it was, I would say, the beginning of having, numerical, imaging among amateurs. And of course, drawing was still an efficient tool to put on the paper what you see at higher resolution. And the idea of this drawing, in fact, was to show that at the very time we had this observation with a radio telescope when we are studying the rotation of the comet, the emission of CO. There was this kind of structure looking like an outburst when showing like the jet was doing showing a full spiral instead of half a spiral. So I had this drawing, and it was by chance done at the very time of this radio observation. That's why I said you can put this in the paper to illustrate that, in fact, maybe something was especially happening on that very date and not on the other dates. But you said it was published in 2018, and the observation was done in 1997, 20 years before. So we have to look at what we have in the archive. I mean, if you now we are interested in how a comet looked like in the 50s or in the 40s, we have only drawings from that time.
Okay, Casper?
Yes, if you're, let's say, starting your career in comets again, is there any particular figure in the field of cometary science, one of the a renowned expert from the past that you would choose as a mentor starting today? Is there somebody you look up to in the field?
I'm not sure. I mean, sometimes you happen to work on comets because there was I happened actually to work on comets because there was this opportunity to do a PhD on comets. I could just remember that I was looking for doing a PhD on something on solar system science. At that time, I was fascinated by André Braic. I don't know if you know his name. Unfortunately, I mean, he passed away like a few years ago, but he was very well known actually in France. Even probably some foreign people knew him by his way of speaking very fast. Some were talking about bike speed unit when you are talking. So I don't know if you ever heard about him. And he was fascinating. I mean, attracting a lot of students towards planetary science. And after, so we spent a few evenings talking with him and to know with which team we could do a PhD. And I happened to go to the team where Dominique was working. But I was not especially interested in comets at that time. I said, why not? I had observed comets before. And for any reason, I don't know for which reason, in the queue of the canteen, Dominique came to me. I said, actually, it was a training period. It was not the PhD, yes. It was just, I had a training, I could get you for a training period on comets if you want to do your master in astrophysics. No, yeah. Before the PhD, and that's the way I became involved in cometary science. But at that time, I was not thinking of well-known, I mean, cometary scientists. Just because, well, why not? Comets are nice. Why not doing science on comets? But and I learned, I mean, after about Oort, about Whipple, and also, I mean, contemporaneous, I mean. Scientists involved in comets, but I was not inspired by a cometary scientist before, I would say.
All right, Carl.
Yeah, so most of your professional work has been, radio and millimeter, submillimeter observations of comets. And, those are wavelengths that most people aren't really familiar with. I mean, most people are more familiar with, the visible and maybe near infrared. So just kind of tell us a little more about how those observations come about. Like, what do those observations look like? How do you reduce them? I mean, you're not looking at images. Is it more like spectroscopy?
Yeah, it's very like spectroscopy. I mean, we are getting actually now amateurs a bit involved in doing a spectra of comets. Millimeter to submillimeter radio science is just, at that time, now it's mostly spectroscopy. So sometimes it's actually easier to work on this data because it's one-dimension data. You don't have also an image, so it's not as heavy, I mean, data, except now that you're using big facilities like ALMA when you are doing also images, it's picking gigabytes or terabytes of data, so it's getting more complex. But at that time, I could make a significant difference between I would say amateur science, not amateur astronomy, looking at comets, making images, and doing more robust science with spectroscopy. When you look at composition, you look at molecules. So you're doing science, it's just numbers. It's something you work on with a computer. It's not images. So I could make the difference between amateur stuff and professional stuff. But I was also interested in, I would say, in chemistry, because that's the way you do chemistry on comets. You learn about what is comet made of, and that's why I'm still interested in this. And it was really, I mean, the 90s and early 20s until even more recently. I mean, it's kind of fascinating discovering new molecules in comets. I mean, I would say I was kind of the first to discover ethanol, I mean, alcohol, the one you drink in comets. It's also, I mean, something to make fun of, but but yeah, it's you learn about the composition of comets, and that's very complementary to the images of you get. So that's a way I'm still interested in doing I mean, science on comets. More recently, I'm studying molecules like formic acid and isocyanic acid, which are, and I'm still interested in this. I can't tell exactly why, but that teach me more about what our comets are made of.
Yeah, I think a few years ago, it even made the news, if I'm not mistaken, whenever you first found ethanol. I believe it was in a comet, one of Terry Lovejoy's comets, right?
Yeah.
And it made the news as the drunken comet. Right? I saw the headline, so it was really funny.
Yeah, right. Sometimes you like to play a bit with this, I mean, kind of story, because it gets attractive for the media and so on. It's a way to advertise our science also. I mean, you have to at some point.
And Charles?
Yes, following up on that, at what distances, heliocentric and geocentric distances, do comets become radioactive in the sense that you can actually make observations? Is there a limit? Does it have to be a certain distance from the Earth or from the Sun for this to happen?
Yeah, that's a good question. You have to tell to people who are interested in knowing, I mean, the composition of comets. I think a comet is radioactive probably at the same distance that is infrared active. I mean, you need a comet to be bright enough to be able to detect those molecules, because in fact, you have to understand that what we do in the radio, which is not so far from what you do in the infrared, is doing spectroscopy at a very high resolution. So you need a lot of flux to spread, I mean, the spectrum on a very large band. And typically, I will not give really a distance, because it depends both on the distance to the sun, because if a comet is too close to the sun, you will destroy quickly the molecules, so the signal will decrease. But and of course, if it's closer to the Earth, I mean, the signal will be stronger. But more or less, it's also correlated to the brightness, in fact, of the comet. So typically, I would say in the infrared, in the radio, maybe also when you do spectroscopy in the visible. Someone, I mean, told to Dominic once, I mean, if I see the comet with binoculars, then I can detect it with the radio telescope. And I would say it's about true, I mean, for the infrared studies and for even probably visible spectroscopy. So you need a bright comet visible, I would say, with binoculars. Let's say in comet brighter than 10 magnitude typically. But of course, you have exceptions. You have some special comets like comet Schwarzschild-Bachmann 1 or maybe Bernstein, which is very far away, in which we may detect, I mean, molecules like CO quite far from the sun, because in the radio we are sensitive, actually maybe more sensitive than infrared. So there are some exceptions because these comets are kind of special. But typically, we are not interested in 19th, 18th, 17th magnitude comet, but comets that are more in the range of visible to naked eye to visible to binoculars, I would say.
Hey, Mike.
Yeah. So the molecules that you observe at those millimeter and submillimeter radio wavelengths, of course, contribute to the cometary activity. So can you give us a short overview of the molecules different than water, than you are involved in the cometary activity?
Sure. Yeah, but actually, I've written this also in a chapter, in a book chapter that should soon, be published next year on comet chemistry. There are typically 3 molecules that plays an important role in the activity of comets. I think there's a consensus among most of the people that there are these 3 molecules. You have, of course, water, as you mentioned. You have CO2, and that's unfortunately we don't observe CO2 in the radio, and we don't observe it from the ground also. So we have to observe it, for example, with James Webb Telescope, or there was a few missions before, like Akari. And apparently CO2 is an important driver for activity of comet, even comet sometimes close to the sun, because CO2 can lift ice, and the water is coming from the ice lifted by CO2. But at distance, intermediate distance, I would say maybe between 2 or 3 or 4 or 5 astronomical units from the sun, maybe CO2 is overtaking the activity of water sublimation. And CO is the molecule that we detect more easily in the radio, also detectable in the infrared and in the UV, which is, driving the activity of comet up to a large heliocentric distance. We have detected it in comet Hale-Bopp at 14 AU. It was detected with James Webb in comet Bernstein at like 20 AU. So, and in other comets, it has been detected far from the sun. So I would say these are the 3 main drivers, and also because CO2 and CO apparently can be quite abundant compared to water. When the comet is close to the sun, when you have a good idea of what is the bulk composition of the comet, because these molecules like CO and CO2 can be 20 or 30% relative to water. So if the water is insufficient to drive activity because it's too cold, there's enough CO or CO2 to drive the activity of these comets. And I think these are the main molecules, because all the other molecules have a very small abundance and they cannot drive the activity by themselves. And they are most likely embedded in the ices of CO2 of water, or maybe CO. For nitrogen, maybe we don't have a very good coverage of nitrogen in comets, so I will not say much about nitrogen, molecular nitrogen, maybe also molecular oxygen, but we don't have enough data on this.
Yeah. Okay.
So Nicolas, what is this book that you're talking about coming out next year?
Yeah, it's Comet's 3 books from a University of Arizona Press. Most of the chapters are already on archive. you can. I was responsible for the chapter on chemistry, so everything about comet composition measured from the infrared, from the radio, from the UV, also from in situ with mass spectroscopy. In the beginning of our chapter, we list the various molecules responsible for the activity of comets. So it's a scientific book, but it's also designed also for students in principle, and it's a good overview of everything about comets. And the previous, Comets 2 book was published in 2004. So.
Okay. Casper?
Yeah, regarding comet chemistry, I would like to know, what do you think about, of course, this extraordinarily different comet that we had a few years ago, which is C2026 R2 Pan-STARRS. And, it seems to me that it might have some things in common with Comet Morehouse and Comet Humason in terms of very high abundance of carbon monoxide relative to water. Do you think those 3 comets, even though they're not related orbitally, would you say that they're a subcategory or subfamily of comets from a chemical standpoint in the solar system? And also, do you talk about that in the book about these comets in Comets 3?
Yeah, I think I talk a bit about this. But of course, yeah, this comet is very special, and I don't know what to say about it, but I wrote a paper and I call this blue comets. I'm probably not the only one to call them blue comets, because I put comets in the plural because I think comet Humason in 1961 and probably comet Morus in 1908 are also similar. Comet Humason is really looking like a comet 2016 R2. And of course, we had the opportunity to study this comet in detail. I did it from the radio. Some you did also. I think you do the observation with RO telescope.
Yeah, with the SMT 10 meters.
Yeah, and it was also studied in the visible and the infrared. And the composition is really completely different from any other comet we have observed to now. I would say. Mercury is more like Jupiter when you compare this comet to other comets. It's the ratio of some molecules like water to CO is orders of magnitude difference. It's very fascinating, and that's why we say this comet must have been either accreted somewhere else in the solar system, or the other option we said it may be a piece of a bigger object that was differentiated, but for me, it would be very interesting to see one of these comets from close with a spacecraft, because it looks so different from other comets that, and unfortunately, these comets are very rare. I mean, I think we have seen maybe 3, 4, 5 comets of this kind in 1 century. We have seen 2 interstellar objects. It's and they are more different from other comets than the interstellar comet Borisov. So yeah, we have in our solar system more diversity than maybe in our galaxy. So, I'm very interested with such objects. I mean, it's, next time there is one, we must do what we can to study it in more detail. So.
Carl?
Yeah. So, observing molecules in these various comets, what are the questions that you're trying to answer? I mean, it's more than just, what are comets made of? I mean, these questions probably give you insight into the formation of the solar system, as well as just the molecules you'll find in the interstellar medium out there. So I guess the big question is, what is driving the study of comets at these wavelengths? What is like the biggest open question that you're trying to solve?
Well, we are always looking for an answer to this and to know what we can put in the introduction of our papers. And yeah, I would say, I mean, if the problem, I think, after having tried to measure the composition of tens, maybe 30 or 40 comets, is that we still don't have a very good view of the composition of comets, because there's one thing. I mean, we have now an overview. We know about 50, 60 different molecules that we can find in comets. But still, the ratio, I mean, for some, we have an uncertainty of more than 1 order of magnitude. Either it's the diversity or it's a bias due to the measure. So I think the first point is to know actually this composition, because I'm not sure we really know. And I see models that say that if you see 20% of CO relative to water coming out of the comet, doesn't mean that there's 20% of CO relative to water inside the comet. So there are still many open questions on the composition themselves. And as we mentioned after, of course, the big idea is that our system, solar system, was born 5 billion years ago. Most comets, played a major role in building blocks of giant planets core, or maybe bringing also, molecules to the early Earth. I mean, we know that we don't know yet if water ocean came solely from comets or from other source, but for sure, comets did bring water on the Earth, and it didn't only bring water, but also many other molecules, the one we see now. So at least from the composition point of view, is also to answer what was on the Earth 4.5 billion years ago. We know that probably it came from the comet that we can sample now. And another point behind this also, if I'm talking about composition, we have also this more complex thing, which is isotopic ratio, which tells us, actually, if a molecule is similar in the comet or in the Earth, because we know that the isotopic ratio, let's say for the best known is semi-heavy water compared to light water, I would say H2O versus H2O. And the point that, this couldn't have changed since the molecule was formed 4.5 billion years ago. So this is the best clue to say if the water from the comet and is the same that the water from the Earth. And that's for the case of water when we're talking about isotopic ratio in water, but also for nitrogen. The nitrogen that we have in our atmosphere, it's not the same as the nitrogen in comets. Why? But it's not the same also as the nitrogen in giant planets, and so it's still different. So there are still many open questions, and that's why we are talking about a special comet before Blue Comet. It looks like there is diversity in comets. So another open question is, do we inherited, our organic matter on Earth from a certain category of comets? Some say it may come from some asteroids, hydrated asteroids, which are some more primitive asteroids. We have diversity in comets, so we have also to understand this diversity and maybe to help answer the question what came from comets on the Earth.
So we also have these interstellar objects. We had Oumuamua and Borisov.
Yeah.
And so these are objects that not only formed in a different part of the galaxy from the comets that are around the sun, but possibly also a different age. And do you expect those to look different? And are those differences something do you think we could actually detect? Because we already have this great diverse, we got this diversity among comets that we know formed with the sun. How easy or hard do you think it would be to pick out interstellar objects compared to the objects we have here?
Well, there are 2 points. First, the difficulty of having a good interstellar object in which we can measure the composition with high precision. As I said, we haven't seen interstellar comet visible to the naked eye or in binoculars for ages. That's one difficulty. And after, about the diversity, you mentioned that the molecules we have in the comets are somewhat heritage from the interstellar medium, because the comparison shows that the ratio, at that point we are talking about orders of magnitude, probably accuracy not within a factor of 2 or a few percent. It's not so different in the comets and interstellar medium, at least the near interstellar medium closer to the sun. So that's why actually what we found in comet Borisov is not so surprising, because it's not so different from the comets of our solar system. But of course, it tells us that in fact that the diversity may not be due to the place where you are formed in the galaxy, but probably the time where you are formed inside your solar system or the distance from the star. So, what it turned out that in fact comet Borisov could have been born in our solar system, we wouldn't have noticed the difference.
Okay, Charles?
Yeah, I'm going to back up for a moment and ask you, during your radio career, what has been the most interesting radio comet that you have observed, and why?
That's a good question. It's not so easy to answer. We mentioned earlier on, this comet, special comet 2016 R2 parent stars, which was a very special one. Also, it's of course fascinating to discover new molecules. So, of course, you always want more. If you have the brighter comet, if you have the best weather, and you're kind of sure you can detect more molecules, and of course. Like on Comet Lovejoy in 2016-15, when I managed to detect, alcohol, it was a kind of reward. Just you search for new molecules and you find the one which is the one that says something to everybody. So, so I would say that was a kind. Actually, it came like I would say nearly a Christmas gift. This comet. Because actually, this comet was discovered not much before it went close to the Earth. It was discovered, I think, in August 2014, and we observed it in 6 months after. And just a few days before Christmas, I decided, well, there's an opportunity. Maybe we shouldn't miss it with with the Hiram 30-meter telescope. It was well after the normal deadline to observe it in January. So I put a DDT, I mean a target of opportunity for proposal sent to the director of the telescope like a few days before Christmas. And he said, okay, like 1 week after. And it was too late, I mean, to organize a trip to go to the telescope. So I did more or less the observation remotely from my office in Meudon. So in the second session, it was done by a colleague of mine because we got 2 observing sessions, but the first one was done kind of remotely because I didn't have time to go there, so unfortunately. But I got a very nice data, and that's why I said it was in early January. It was kind of a gift, a Christmas gift, because in less than 1 month, nearly a matter of 3 weeks, I decided so we should go to this comet, and I detected a new molecule like 3 weeks after. So that's a kind of a good souvenir of radio observation.
So every once in a while, we have a comet that comes close to the Earth that's discovered right before close approach, like Arasaraki Alcock in 1983 or Yakutaki in 1996. So is it hard to get radio telescope time on really short notice, like within a week?
Yeah, that's also a good question because nowadays we are getting a lot bigger and bigger facilities like ALMA, like VLT, like many other telescopes. But unfortunately, the bigger the facility, the more responsibilities, the more administrative is the way, I mean, to go through the various process to get time and more complexities on the. So we have to train a bit also the team on the TAC. I mean the people who are reviewing the proposal to what is cometary science and what is the unexpected an unexpected comet, but that maybe in many cases you get the best science on the most unexpected event. And I would say that the Hiram 30-meter telescope, I mean, got its first light at the time of Halley's comet. So they are kind of used, I mean, to observe comets with this telescope. And they know that comet can arrive on late notice. And they have this nice flexibility that you may ask time on a very late notice because you have an outburst of a comet or you have a new comet, and you manage to get time on short notice. Another example was Comet Holmes. I don't know if you remember this big outburst it had in October 2007, I think, yeah. Mm-hmm. And we managed to get the first spectra like 24 hours after the outburst, and after to sneak in the second. So in some time with this smaller facilities, which is still quite a significant facility because the antenna is 30-meter diameter, they have the flexibility to get you, I mean, target of opportunity time on very short notice. And that's what is important also in general astronomy, is that to have also facilities, not necessarily the bigger one, but we can react very quickly on such kind of event. Of course, it's valid for cometary science, but I'm sure people doing gamma ray burst on other events are also interested in such kind of flexibility.
Yep. Mike?
Yeah, you know, for me as a purely visual observer, it's interesting. Do you have any influences on when it comes to radio observations or those different wavelengths? You know, with a visual observer, we have light pollution, we of course the weather. So anything that hampers your observation?
Well, there are 2 things. Recently, not for visual, I would say for people doing, I mean, more digital imaging, I mean, doing astrometry. Recently, I mean, I'm using the very recent astrometry done like a few days before, 1 day before, to check, I mean, the ephemeris, because one issue we have when you do radio astronomy is that you need to know the position of the nucleus within, if possible, 1 or 2 arc seconds, because you have you are like observing with a single pixel, which is 10 arc second or even less in diameter. So if you are off by 10 arc second, you miss most of the signal. That's one point.
Yeah.
But
that's a problem with the close approach comet too. That's discovered right, to go
in
after
addition,
away when you.
Close comet discovered late, can be really off the position quite quickly.
Yeah.
But the other thing you mentioned about visual observation, that all prospects of comet brightness is based on the first visual estimate of their brightness. Sometimes the media, are over exaggerating. What a comet will be like. We have known several examples in the past. I could say, for example, take the example of comet Ison, which actually didn't survive to perihelion, but some would say, some media said a few months before it will be the comet of the century or whatever. But in fact, even if we know that they are exaggerating a lot and so on, it helps to get time on these telescopes. Because if it is attracting media attention because the comet is potentially coming up to be a bright one, the people who are reading the proposal, they've heard about this comet in the media, and they are getting more interested in comets and awarding us time. Actually, I should mention that for comet Ison, I didn't get much data on comet Ison, especially after perihelion, but there was fortunately another comet Lovejoy, 2013 R1, I think, which was quite bright and on which I could get a lot of science.
Casper?
Yeah, so it is often said, and it's also, in a way, my impression that cometary science has advanced the most over the past 30 years, roughly, with two events. One is the appearance of comet Hale-Bopp and all the subsequent studies, spectroscopy, molecular, etc., that have been performed on it. And the other event was, the spacecraft Rosetta that rendezvoused with comet 67P Churyumov-Gerasimenko. So I know this is kind of a vague question, but what do you think, or maybe you wish, will be the next such event or breakthrough, if you wish, in cometary science in the near or mid future?
Yeah, I try to think about this, and either you have to be ambitious or it's hard to expect this. But I would say the next event will be to bring back a big sample of a comet. And there has been, some studies, but to bring back a cryogenic sample of a comet. That is to say, to bring back a sample kept at a very cold temperature, if possible, the temperature at which it is taken. It's possible also not from the surface, but from a bit beneath the surface of the comet, and to know exactly what is probably the structure, but also the comet ice is made of exactly. Mm-hmm. But of course, it's kind of a challenge. But I think when we had this mission in Rosetta with the challenge of landing on a comet on a terrain you would know nothing at all before. We didn't know even the shape of the comet. Actually, we had a wrong idea of the shape of the comet. And we managed more or less to land on it. So why not being able, to take a sample of a comet and bring it back to the Earth? It's probably not as difficult as from Mars because you don't have the problem of gravity, but there are other issues. But I would say probably this is the next big step. But after, you mentioned comet Hale-Bopp, we can have also unexpected big opportunity. Just imagine a Hale-Bopp interstellar comet coming close to the Earth. That will bring us also a lot of interesting information from another solar system, whatever.
Yeah. Carl?
So you were part of the Rosetta science team and published quite a few papers now with data that was taken with the MURO instrument. What did you learn about 67P being so close to the comet that you could never have figured out from the ground using our large remote radio telescopes?
Well, I would say, so I worked a lot on the MURO instrument, which is a small radio telescope that was on board of Rosetta. but it's only 30 centimeter diameter.
Mhm.
It's it's not 30 meter diameter. It's 30 centimeter. So we had a kind of limited sensitivity. So I did all I could do. I mean, from this data to retrieve at least, I mean, the behavior of the comet from the two perspectives. I mean, the evolution with time, and also the outgassing pattern. In more precise words, I mean, where the comet the molecules are coming from the comet and in which direction they are coming. So to learn from in situ how, I mean, outgassing is taking place from the comet. After, of course, there are some discussion between the result we get with MIRO, with VIRTIS, with the camera OSIRIS, with a mass spectrometer. There are still some discrepancy, and that I don't think I got something which is completely unexpected, but at least I don't know exactly how to summarize, but at least we know we sampled, I mean, the inner coma, I mean, within the first 100 kilometers, and we saw on this comet, because I think 67P is one example, but probably not representative of all comets. We saw how it works on, I would say, kind of old periodic comet when you have this jet, and we discovered that, in fact, this jet is not really a jet coming from a place on the surface. It's just due to the rotation state of the comet, probably not so dependent on the shape of the comet. But I managed, I would say, from this data, I mean, to couple at the same time composition, evolution with time, and also, as I said, I mean, outgassing geometry, where the molecules are coming from. And we learned that actually there's a kind of more pristine, I mean, place on the comet with the south pole, which is exposed to the sun at perihelion, while the other part of the comet is more processed, I would say, due to activity taking place far from the sun when the water is not outgassing so easily. And we learned that although the comet may be relatively homogeneous as a whole, locally there's a lot of heterogeneity due to the various, I mean, physical processes, and I think that's what, I mean, the mission told us, that you have to be careful when you measure something at one point, one place in the orbit at time, that if you want to know if it's representative of the bulk composition of the comet, you have to be careful.
So Nicolas, if you could go back in time, pick a comet that you would love to be able to see in the past with today's modern equipment.
Well, you know that we got some quite nice comet with Hale-Bopp, and there's no many. But we mentioned earlier on, I mean, this comet Morose in 1908, which is apparently a kind of this blue comet that came also relatively close to the sun. So it was also close enough to outgas probably more water on other species than comet 2016 R2 or Humason. Even also Humason will have been interesting, but maybe this comet Morose with a modern technique will have offered us a quite interesting view on, as I said to colleagues, don't take 67P as representing all the kind of comet we have in the solar system. And having had, for example, lots of techniques like James Webb and IRAM and so on, HALMA, to observe this comet Morose, will have offered probably a quite different view of a comet, letting know other people that a comet can be very different from one to another. So,
how about one of the sun grazers like Kawasaki in 1965 when it got further away from the sun? Wouldn't that be of interest?
Well, I think a sun-grazing comet is kind of different, science. Because when you are so close to the sun, then you start sublimating the refractory part of the comet. So of course it's interesting, but I was talking recently to Emmanuel Géhin, who wrote a paper on the detecting nickel on iron on comets distant from the sun. But it's not the same iron and nickel. I think that even the ratio is not the same that was measured in Nikeyaseki very close to the sun, because it's not coming from the same part of the comet. These are actually what they call carbonyls. In fact, it's iron and nickel connected to CO molecules, which make what we call carbonyls, which are not, the iron nickel you get in the solid phase, in the sound-like, material you have in the comet. And of course, sun-grazing comet, they show different things that you don't get in other comet. Not going even to sun-grazing comet, I noticed recently, we have noticed for a few years that when a comet gets within 0.3, more or less 0.35 AU from the sun, you start seeing a lot of sodium going out of these comets. So beyond 0.3 AU from the sun, you starting seeing other species. And of course, this is complementary to what we are doing. But we get into more visible spectroscopy in that case, because we have done some observation of comets at 0.1, 0.2 AU in the radio, but it's kind of difficult to detect anything in that case. So I give the hand to visible spectroscopists for this.
Okay. Any closing thoughts, Nicolas?
Sorry?
Any closing thoughts? Anything that?
One thing I learned about observing both visually and also in the radio is that comets are so different from one another. It's very difficult to see two comets that are very similar to each other. I would say comets are like human characters, like people, their own characters are different from each other. There's a huge diversity in comets. That's what is fascinating, because every new comet will be different. I want to give the example of this comet 12P Post-Brooks, which has this very special behavior with this recurring outburst that we haven't seen so often in many other comets. So every comet is different, and that's why I like observing comets, because there's always a lot of suspense with comets. I don't know what you think about this, but that's what is fascinating about comets. There's a lot of surprise.
Yeah. Especially when you get an interstellar comet like Borisov. Then, yeah. Someday we should get an interstellar comet that's bright, a big object. They definitely should happen. It's just whether it happens in our lifetime,
Yeah. It's a matter of statistics.
It's possible that some of the comets of a couple millennia ago, that we don't really have orbits for, were interstellar comets. Sure. We have no idea. Yeah. Okay. Well, thank you, Nicolas. We appreciate your time, and I think that a lot of our viewers will appreciate hearing what you have to say.
Yeah. Hope so.
Yep. Okay. So that's it for today. We'll sign off here.